Really nothing to do with the direction the comet is moving. It's not like the tail is like behind the comet, like a racing scarf on a Indy 500 driver or something like that. It's simply going to point away from the sun. So when the comet moves towards the sun, the tail, points opposite the direction of motion. But when the comet moves away, it points in the direction of motion. So that's a little something that a lot of people don't expect. All right, so let's just talk briefly about meteorites and asteroids here. Again, we're not going to go into a lot of detail here because this is just a survey chapter of the solar system. But the connection is that asteroids and comets actually give rise to meteorites, which are the small specks, well, they're not all small actually, but most of them are very small, that enter our atmosphere and burn up in our atmosphere to create the shooting stars that we see. But the larger ones actually make it to the ground and can be analyzed. And we can learn something about extraterrestrial compositions by analyzing meteorites that have landed on Earth, because they're not from Earth, they're from elsewhere, and so they're going to have different chemical compositions which we can use to learn about the bodies that they came from. All right, so as I say here, if we talk about meteorites, now meteorites are bodies that have hit the ground on Earth. They're meteors until they hit the ground, then they become meteorites. So if you look at the little UPC label very closely, and there's some good video of this, you can actually see it change. The UPC label on the object changes from meteor to meteorite just when it hits the ground. You can actually see that. So if you're buying anything on any one of these on eBay, you want to actually buy the meteorite, not the meteor, because the meteor is still in flight, and if you buy that, it'll hit you. So you don't want to do that. And there's three main types of meteorites. Silicon, iron are the main ones, and we also see some carbon meteorites that are called carbonaceous chondrites, carbonaceous chondrites, not carbonaceous chondrites. They used to think it's like, check this, carbonaceous chondrites. Anyway, so most of these bodies that we find on Earth, the meteorites, are silicon or iron. They're stony composition, the silicon ones. They're stony looking objects. Or they have some iron in them. Very few have carbon. Now, it's interesting to contrast what we see in meteorites on the surface of the Earth with the distribution of compositions of asteroids. Now, asteroids are large bodies that orbit around the sun. So meteorites and asteroids are actually two different things. There's a connection, but they're two different things. Asteroids are these big bodies that can be up to 1,000 kilometers across that orbit mainly in the asteroid belt between Mars and Jupiter. So most asteroids are between Mars and Jupiter right now as we speak. Most of them are there. But if they smash together and turn into smaller fragments, then you can get meteorites, which can be fragments of asteroids that fall into Earth's atmosphere. But that's not the only way you get meteorites. You also can get them from comets that have decayed away. But anyway, okay, so the asteroids are divided into three groups. The C-type asteroids are carbon, S-type asteroids are mostly silicon, and then you have M-type asteroids, which are mostly iron and nickel, and the M there stands for metal, so they're mostly metal, and mostly iron nickel. Now, it's interesting just to say a little bit about where these guys came from and how primordial are they? Who has the primordial bragging rights in a situation like this? It's pretty much the carbon asteroids. Pretty much are the most primordial. They are predominantly in the outer solar system, and they're mostly carbon, and we think that that's material which has not been reprocessed, because when you combine carbon with other things, it tends to react, it tends to melt, and you don't see pure carbon bodies anymore if they've smashed together with other things. So when you see a carbon-rich asteroid, it's quite primordial, as we say in the business. The silicon asteroids are rocky, stony bodies that have some reprocessing. They've probably come close enough to the sun for some chemical reactions to occur, driven by the solar heating, which has led them to become a little bit more like earthly rocks. And then we have the M, which are mostly iron nickel. Now, iron and nickel do not actually just lump together in the gases from which the solar system formed. The only way you're going to concentrate iron and nickel is in the core of a much larger body that formed and existed for a while, and then got blasted apart by a collision. So the M asteroids actually represent highly processed material that was probably the core at one time. millions or billions of years ago, was the core of a planet which failed to form completely because it got walled by another planet that was trying to form. The formation of the solar system was a chaotic process. Lots of collisions happening, and bodies could exist for millions of years on their way to becoming a wonderful planet, and then bam, they get completely pulverized by a collision. But they may have lived long enough to form an iron core. And then when that gets pulverized and flung out, you get these M-type asteroids. Okay, so the last thing I want to point out here is that if we look at the statistics, everybody loves statistics, right? Now the meteorites are mostly silicon and copper, with silicon and iron without much carbon, right? The meteorites are mostly silicon and iron without much carbon. But then you look down here and I'm saying most of the asteroids are carbon, only 15% are silicon, and around 10% are metallic nickel iron. So that sort of flies in the face of what I'm saying here, which is that the carbon meteorites are rare, whereas the carbon asteroids are the most common. So there's sort of a little bit of a jarring disconnect right there, right? Well, the reason for this is because the carbon asteroids primarily exist in the outer solar system. And it goes along with the fact that they're not very reprocessed. Reprocessing occurs when they get near the sun and they can heat it up a lot. So these unprocessed objects tend to be at large distances from the sun. We're not at a very large distance from the sun here on Earth. So when these bodies collide and form meteors, carbon meteors, very few of them get to the Earth because they're mostly way, way out in the solar system. So that's the reason for the disconnect, is because the carbon asteroids, most of the asteroids are carbon, but they're mostly in the outer solar system, in the asteroid belt. Very few are in the inner solar system. The ones that get in here, to our distance from the sun, are mainly the silicon and iron, even though they're relatively rare if you look at the statistics of asteroids in general. Now, asteroids in general means you're looking at all the asteroids in the solar system, no matter where they are. But if you look at the ones that are near the sun, they're actually mostly silicon and iron, not carbon. So that's the reason that we see mostly silicon and iron types of meteorites. We do see some carbonaceous chondrites, which are meteorites that are mostly carbon. There's some, but they're very rare, only about 5% of the ones that land on Earth's surface are carbonaceous, whereas they're actually comprising 75% of the asteroid population. So that's the spatial, regional disconnect that I was talking about. So I will ask something about that on the exam, having just invested a lot of time talking about this. So you're lucky because you all are here. You'll know this is going to be on the exam, not on practice exam. Yes, sir.
Question about comets. What happens to comets that have gone around the sun numerous times and have melted their ice and
Okay, perfect. Thank you. Well, it links back into this idea of meteorites. Well, not exactly, sort of meteorites. The granules that are mixed with the ice in comets, which I said are like dirty snowballs type things, those little granules are mostly of the stony type of variety. And so what happens to comets when they've gone around the sun a number of times, they lose a lot of their ice. Because every time they get close to the sun, they lose some ice. When they go back into the outer solar system, they don't regain that ice because there's no weather conditions in the outer solar system. It's just a vacuum, right? So when they go back out to the outer solar system, they freeze solid again, but they don't get any extra ice to replace the ice that they lost. So every time they cycle into the inner solar system, and remember, they've got these very elliptical orbits, so they come into the inner solar system, they go way out. When they come in, they melt, the tail is produced, they lose some ice, and every time they cycle, they lose mass. So as our friend there suggested, after a few million cycles around the sun, there's no ice left. And all that's left is a swarm of these little dust particles that will mix with the ice. They don't melt in the sunlight, but the ice does. So what you end up with in the original comet orbit is a swarm of these little particles following the original comet orbit, like ghosts of comets past, just to link in with the upcoming holiday season. Ghosts of comets past, so these little particles. And when the Earth goes through the path of that original cometary trail, we're not hurt or anything, but we do end up getting walloped by a lot of this leftover cometary material, and that forms the asteroid swarms that you hear about occasionally, like the Perseids, that's the asteroid swarms, not asteroids, meteorite swarms. like the Perseids, for example, that happen a certain time of the year when the Earth moves through the orbit of this ancient comet that's actually gone, but its sort of skeleton, if you will, remains. That's a Halloween thing. Skeleton remains. So we were haunted by this ancient comet, and when we go through the trail, we get a swarm of shooting stars, which are just the leftover dust particles burning out. Okay, so anyway, here we have, actually, speaking of things burning up in the atmosphere, here we have a body entering into Earth's thick atmosphere there. And what's going to happen? I warned you. That's what happens. Well, it doesn't always make a sound like that unless it's really a massive object. The smaller shooting stars just burn up in the atmosphere, and we see shooting stars in little streaks. But if it's massive enough, which is above a few kilograms, it'll make it to the ground, and then we can pick it up and study it. Yes, sir. Yes? I couldn't quite pick that up on the exam. I couldn't quite pick that up.
Carbon or not?
Our answer is carbon or not carbon? That was good? Oh yeah, if I ask you, our asteroids mostly carbon or not carbon, you say mostly carbon. Because when I say our asteroids, whatever, I'm talking about all the asteroids in the whole solar system, you know? Now, if I talk about the ones that are close to Earth, it would be a different answer. It would be mostly silicon or iron. See? And that's again why the meteorites that actually make it to the ground are mostly silicon or iron, not carbon. Carbon dioxide is farther away. Thank you. Okay. I should have like 10 questions on this. You guys really get the bang for the buck for being here.